this educational series. As you know, there are the first Wednesday of every month. Natalia, Liane, and Ivan will be presenting Causal learning. There'll be teachers at 4, so we can have them one this time. Floor's yours.
Thank you. Hi, everyone. My name is Natalia. I'm a first year PhD student. I'm supervised by George. And today we're going to be talking to you about causality and causal machine learning applications in healthcare. So I'm going to give a bit of an introduction to causality and kind of give you a foundation in understanding causality as a whole. And then Liane will be talking about some classical causal machine learning tools, and then Zhenshan will finish off with some causal deep learning. So this is a slightly different what I picked to demonstrate the importance of causal understanding in research. So from this graph, you might be tempted to draw the conclusion that more chocolate means that a population might receive more Nobel Prizes. But I think as scientists, we all have kind of an intuition for the fact that correlation does not imply causation. And so causality is kind of a formalization of this thinking, and it's a study of how things can influence each other, not just how they correlate to one another, but also how changing one can change another. So causality goes beyond observing and asks what happens if I do something, or what happened if I had done something else. So here I just put some statistical questions that most of us, I think, in the department are focusing on answering. So things like, can we predict the diagnosis of patients using their MRI or other modalities of medical imaging? Or can we predict the probability of disease progression given some patients' medical history? However, causality allows us to move beyond these correlations and allows us to ask questions about the etiology of the disease and personalized questions for specific patients. So, for example, what would this patient's MRI scan look like if they did not take a specific drug? What can be done to reduce the risk of complications during surgery for an average patient or a particular patient? And I wanted to introduce Judea Pearl to you. So Judea Pearl is kind of one of the most foundational figures in causality. He's formalized the field to be what it is today. And he introduces causality and a way to look at your data and the questions that you want to ask about your data through this ladder of causality. So at the bottom rung, we start with association. So this kind of asks, if I observe a specific variable, what is the chances that I observe something else? So this relies on correlations in the data, and it's kind of where most normal machine learning that we work with lies. So we are looking mostly at these kind of correlation patterns in the data and asking, given that I observe this, what is the probability that I observe something else? And then at the next rung, we have interventions, which ask what happens to the system if I intervene upon one specific variable? How does the rest of the system react? And this relies on more causal knowledge about the system than the previous rung. And then finally, we have counterfactuals, which is the final rung of causality, which allows us to ask specific hypothetical retrospective questions. So given that this specific thing happened, what would have happened if I intervened and changed that variable to be something else? So this is retrospective in the sense that it looks back at data that has already been collected and observed and asks what would have happened if things were not as they were, actually. And so this allows us to look at specific personalized models for specific patients. Yeah. And so I wanted to introduce causality and formalize it using something quite simple. So looking at treatment effects. And so here we have a system where we look at a patient who either progresses in their disease or doesn't progress in their disease, given some specific treatment. So in order to understand the causal effect of the treatment, we can find the difference for a specific individual in their outcome when they were treated and when they were not treated. And if we want to look at the effect of that treatment on a whole population, we can calculate the average treatment effect in terms of patients when they were treated and patients when they were not treated. But obviously, you can't really observe a patient both when they're treated and they're not treated. They're either treated or not treated, right? So in an ideal scenario, we'd be able to have something like this. So a data set where each represents a patient and we observe their outcome under treatment and under no treatment. And then we find the difference between those outcomes and average them and find essentially the average treatment effect. Obviously, in reality, this is not really what we observe. We can't observe these patients when they're treated and not treated. So what do? We turn to, if we can, to randomized control trials. So these trials allow us to randomly assign patients to either a treatment group or a control group. And this allows us to remove bias and makes the treatment and control groups equivalent. In causality, this is called the exchangeability assumption. It means that if you were to swap these groups, the average treatment effect would still essentially be the same. And it means that we can estimate the average treatment effect directly. So given some treatment, we can look at these two different populations, even though they're not the same people, we can say that they're equivalent and calculate the average treatment effect that way. In most settings, it's quite realistic, so we can't give patients that are sick, not give them drugs if they're sick, or ask them to do things that are not good for them. So especially in healthcare, this is not really feasible a lot of the times. So let's say we're not doing a randomized control trial, but we're looking at how a treatment affects lung cancer. And so I want to estimate the average treatment effect for this treatment on lung cancer, but I find that actually age can affect which treatment a patient is assigned, and it can also affect their probability of developing lung cancer. So in this case, average treatment effect calculation no longer holds, and we need to control for age as a confounder. I'm sure many of us are familiar with confounders and controlling for confounders, but causality allows us to formalize all these concepts and bring them in together and understand the system as a whole. So I just talked about confounders, but there's also other problems that we can come across. So for example, colliders in the system where we essentially want to look at the effect of the causal relationship between broken bones and diabetes. And let's say, well, we know that broken bones and diabetes both cause a patient to be hospitalized, or makes it more likely that a patient might be hospitalized. So if we want to look at the causal relationship between the two, but we only look at patients who are hospitalized, so we control for hospitalization, then we might spuriously identify a causal effect between broken bones and diabetes. So I've introduced some of these problems, but I want to formalize causal graphs so that you can kind of dive into the literature and understand all these concepts on a mathematical level as well, hopefully. So considering we have a graph in here, I've added age and obesity as factors into this graph. But if we consider this graph that consists of vertices and edges, so vertices are the variables that we have, and the edges are the connecting causal links. We have parents, which are variables that lie upstream of a child variable. So here we have obesity as a parent of diabetes, and diabetes is a child of obesity. And then every node that has a causal connection to another, the pair of nodes is said to be adjacent. And we also look at paths in causality. So if we want to look at all the possible paths between obesity and hospitalization, we can follow that through diabetes to hospitalization, or we also have a path that goes from diabetes to age to broken bones to hospitalization. So these are undirected paths, but you also can have a directed path. And in that case, we only have one path, which is path one. That's a little bit about the notation in causal graphs. And most researchers in causality look at directed acyclic graphs, and they use them to kind of make a lot of assumptions that allow them to estimate causal effects. So directed acyclic graphs are directed causal graphs that contain no directed cycles. This means that you can never start and end at the same node. And DAGs obey the local Markov assumption, meaning that your variables can be factorized so that they are independent of each other given their parents, or independent of all the non-descendants given their parents. So this is point one in the minimality assumption, which we often use in causality. And then the second point states that adjacent nodes in the DAG are dependent. So as you remember earlier, these are adjacent nodes. And these assumptions allow us to differentiate between two following scenarios. So if we have two variables that are independent, we can test for their independence directly, because we know that if they are causally connected, then we cannot disentangle them in the same way. So I wanted to introduce some assumptions that are made in causal inference. There's a lot of different assumptions that are made in different settings, but these are kind of the most common ones that you need to know about your data, whether you have broken them in your data or not. So the first one is ignorability. So this is stating that there's no confounders in your system that are not observed. So you're able to control for all of the confounders, or all the possible confounders in your system. And then I just mentioned the causal Markov assumption, the local Markov assumption. So every node is conditionally independent of its non-descendants given its parents. And then positivity, which states that essentially there must be some patients who are treated, and there must be some patients who are not treated. So we have non-deterministic treatment assignment. And faithfulness, which states that essentially all the conditional dependencies that are present in your data represent the true underlying causal graphs. And that means that there's no additional dependencies that we can draw from the data that are not present in the true causal graph. And then consistency, which states that the outcome of an individual is independent of the treatments of all the other individuals. So you can imagine that a lot of these are broken quite often, and a big area of research is trying to relax a lot of these assumptions in different settings. And especially in, for example, healthcare, a lot of these do not hold. And then I mentioned counterfactual reasoning at the beginning of the presentation, and I wanted to return to it. So counterfactual reasoning essentially asks what would have happened if things were different. So I've just put here two examples. So given that Hillary Clinton lost the 2020 election, would Hillary Clinton have won the election if she made an extra visit to a swing state before the election? So again, we already know the outcome, and we ask retrospectively, given all the variables that we have and all the information that we have about the situation, what would have happened if we intervened in some way? And with a patient, we have someone who's taken a drug and recovered, and we ask, would they have recovered if they had not taken the drug? So normally we want to, this is again a very ridiculous example, but we want to ask questions. We usually are asking questions. What is the probability that I observe something given that I observe this other thing? So here I've given an example of what is the probability that someone obtains a PhD degree given that they have a beard. And I've given this example where we have 5 different patients with different rows. And for each individual, we have their beard status, their marriage status, their strength, and their PhD graduation status. So usually we're calculating something like what is the probability of their graduation given that they don't have a beard. However, counterfactuals allow us to move beyond that and ask very personalized questions. So given that someone has a beard and that they have a PhD degree and everything else that they know about me, so all these other factors that we have recorded, with what probability would they have obtained a PhD degree had they never grown a beard? And so this allows us to set the beard variable basically to be 0, and all the nodes that are not dependent of this beard are also set to be what they were in the original individual. And then we evaluate essentially the effect on graduation. So you can see that that's not really changed. So I've talked already a little bit about treatment effects and counterfactuals, but we also can use causality to carry out causal graph discovery. So this essentially means that we are trying to identify the correct directed acyclic graph from observational or interventional data. And there's a lot of different tools that you can use for causal graph discovery, and they all use different strategies. And which one you apply to your data set really depends on what you want, what questions you want to answer, and what is the nature of your data. So what is the noise like in your data? What is the size of your data? What do you expect there to be nonlinear relationships between the variables? These are all kind of different considerations that you need to have when you're picking a causal graph discovery tool. And a lot of these are also trying to, a lot of researchers are trying to develop methods that can actually move beyond some of the very stringent assumptions that are usually made in causal graph discovery, because again, it's not very often that we have data sets in real life that obey all these assumptions. And then I just wanted to finish off a little bit with my work. So I'm using causal drug discovery tools at the moment to essentially validate what we know about Alzheimer's disease already. So I'm using the ADNI data set to recover known relationships in Alzheimer's disease. This data set consists of imaging and clinical data about patients. And I'm using fast causal inference, which is an algorithm that is a modification of one of the ones I previously showed, and it relaxes the no unobserved confounders assumption. And given some limited prior knowledge, the algorithm is able to recover the known etiology of Alzheimer's. So, for example, we have ApoE4 genotype affecting amyloid beta, and for example, age affecting your metabolic state of the brain. So next, I'm going to be looking at integrating longitudinal data with also non-random missingness into causal graph discovery to try and improve some of these things and try and improve the causal graph itself and try and give less prior knowledge. And then this is something else I've been looking at, so trying to look at tau protein spread through the brain using tau PET measurements. So we know that the tau protein is responsible for Alzheimer's disease, and we know that it has this kind of prion-like spread through the brain that starts at the entorhinal cortex and moves through to the neocortex. And so using these regional tau PET measurements, I carried out causal graph discovery, and essentially what this results in is a mirroring of the kind of staging that we already know exists in tau pathology. So the BRAC staging essentially describes what regions are becoming tau positive at each stage of Alzheimer's. So we can see that essentially we start out with earlier stages that then tend to affect the later stages of the disease. And I've just put some resources here in case you were interested in learning more. So I really love the book of Why. I think it's a really great introduction to causality. And then if you want to kind of understand things on a more technical level, I recommend What If. And these are some websites. This is just one website here that I think is a really good introduction to causality. And Causality by Judeo Polo is also a very comprehensive textbook in case you want to learn more. So I'll hand over to Liane to talk about traditional. Sorry? Yeah, if anyone's got questions. Yep. Yeah, so
basically, how do you discover? Like, how do you decide what dimensionality should be? You have one with the variations to see which one benefits your data.
so some of them do that. Some of them run. They kind of essentially output equivalent graphs that you can actually kind of recreate your data set as much as possible. But a lot of these run conditional independence tests, and then they follow kind of a lot of rules in terms of orienting the edges. So if we have like two connect, so if we have like three variables that are conditionally dependent on each other, and the first one is not connected to the last one, then we can say that there is no connection there, but it flows in one specific direction. There's just a lot of steps to basically determining the orientation of these causal links that I can outline.
Just calculating.
Independence, yeah.
Yeah.
Yeah. Sorry? You're not comparing them, you're just determining whether two variables are conditionally independent. Usually just independence tests, like there's kernel conditional independence, chi-squared, things like that. So they use kind of quite simple conditional independence tests. I mean, there's a difficulty with biomedical data because you don't really know the ground truth. So a lot of these methods have been tested on synthetic data, and especially the ones that are designed for smaller data sets, they work really, really well on synthetic data sets. But when you try to scale up, especially when you use deep learning methods, you kind of lose a lot of the identifiability guarantees there. Yeah.
certain practice that are expected.
Yeah, 100%. And one of the things that improves causal graph discovery is introducing priors so that we definitely know a lot of things affect each other, and we know like specific variables that have been proven to affect each other. But it's definitely still an issue. But introducing priors definitely helps the algorithms converge better. And also,
What's required?
so it can be different. I mean, it can be something like you can specify saying, I know that there's a causal link between these two variables. I don't know which direction it is, or I can specify, I know that there's a direction between these two variables and it's in that direction. Or you can,
How to do it?
what do you mean?
Well, right. Small. Variables.
Yeah. Yeah. Right now I'm just looking at like normalized output measurements, which yeah. 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 Mhm. Yeah. Yeah. Yeah, I mean, I think the essential thing is having interventional data. So looking at if you actually are able to change a variable, how that affects things downstream, because that wouldn't show up as much as correlation. That's not just rebranding it. But I agree that it's a problem in a sense. But yeah, I think interventions is the way to go. But again, that's not really possible in many cases.
So, that way, it's relying on whereas the causal studies they are slightly both of them language some models like
Do you want to take over?
So what Natalia was doing, it was just introducing all of the concepts that we need to understand and to start applying causality. Now, what I will try to do is just navigate how can we leverage causality assumptions to build machine learning models and actually build as well data-driven models to estimate causal effects. So I want to make, first of all, a distinction between what's a traditional machine learning and a causal model. And specifically because traditional machine learning leverages correlations between the data, whereas causal models leverage causality. So the main difference between traditional machine learning is the fact that with machine learning, what we want to do is predicting the outcomes of something. So if we pay attention to this graph here, we just want to predict what is the outcome of having a treatment or not, based on the data that we already have. So we are not testing different hypotheses. So basically, we are just saying what is happening next based on the previous data that I already have. And we don't distinguish what is correlation and causation here. And at the end of it, what we are trying to do is just predict, for instance, what is the probability score of the disease or even diagnosis of the disease itself. The difference between that and causal models, it's actually the fact that we want to model possible changes that we have in outcomes due to interventions or counterfactual effects that we might have. So this means that what we want to do is model what happens if I change any variable in my system. So for instance, if we look at this picture here, so instead of having just a path that corresponds to not being treated at all,
what happens if now we apply a treatment? And this could be, for instance, the counterfactual we are studying retrospectively, as Natalia was explaining, or just an intervention if we are looking at the moment. So what we want to do in the end with these models is just quantifying the causal effects of doing any action in the system. So the main difference between the workflow that we have in a traditional machine learning model and a causal model, it's actually this first part here. So it's our problem setup. It's where we define what are the outcomes and what are the predictors that we have into account, and also which kinds of models do we want to estimate and how. So if it was just a traditional machine learning model, we would skip this first step here. So in this case, and starting with the formulation of the structural causal structure, sorry about that. What we want to do is, if I want to predict the outcome here, taking the example of blood glucose, and we know that we might or not having a treatment, what is the relationship between the treatment and the outcome that we have? So once we have that, we need to define which kind of model are we estimating and the treatment type that we are applying, and also if we want to estimate this at the patient level or at the group level. So Natalia already introduced the AAT, so basically the average treatment effects, but we might want to have more individualized effects. And here we are on the conditional average treatment effect, where we personalize the model more on the patient or individual scale. Another thing that we can have binary treatments, so it worked, it didn't work, or we might as well be interested on splitting the different treatment effects and the different treatment outcomes that we might have. So improved a bit, it improved a lot, didn't improve at all, so more granularity in terms of the treatment effects. So once we have done that, we go to the last part of our problem setup, which is the assumptions that we have. So Natalia already walked us through all of the assumptions that we might have in the model, but here is where we can, for instance, introduce as well some prior knowledge that we have about our system. And then we have all of the equivalent structure that we would have for a machine learning model. So we need to find and to pick what is the appropriate machine learning model that we want to apply. We evaluate the model itself, look at the prediction scores that we might have, and then we test for robustness. So in terms of the models that we have, and here I split them between mainly data-driven, and when I put mainly, it's because when we are doing causality, we always have some level of assumptions and prior assumptions that we might include in the model, and then parametric models. So starting with the data-driven, I will just talk about very simple ones like propensity score and how can we leverage them both by themselves or between a machine learning or deep learning framework. Then I will move to tree-based methods, and I will finish with meta learners. I won't go into about the meta learners itself. And then I will move to the parametric models. And here we will start talking about Bayesian networks. Natalia already introduced them, but I will give some examples how to apply them to those scenarios. And finally, to structural causal modeling, which will also include structural equations modeling. So starting with the propensity score. So the propensity score, what we want to do with this type of models, it's actually try to create a separation between what are the groups of subjects or patients that have received some treatment or treatment A, B, or C, and the control. So the ones that didn't receive any treatment. So we just want to create this separation between the different groups of subjects. So in this case, these kind of models have two main assumptions. So the first one is that there is no unmeasured confounders, and this still relies on the assumptions that we have for the causal models themselves. And also that all of the subjects receive at least one treatment or they belong to the control group. So there is no assignment for the subjects that we have in the different groups. So the goal of this is trying as much as possible to have what we would have in a randomized clinical trial, which is not always possible. So it's trying to minimize the biases that we have often in observational studies. And one of the benefits of this type of models is the fact that they don't require strong assumptions, apart from the two that I just mentioned, which is try to split the subjects in according to the groups that they belong and maximizing the distance between the different effects per treatment. So common ways of doing that can be with matching, stratification, or weighting. So weighting, it will be just trying to weight the classes and the number of subjects that receive each one of the treatments. Stratification, the same thing, keeping always the balance between the different treatment groups and the subjects belonging to each one of the treatments. Yes.
But if you really have the same values.
Covariates and as well. So basically, we just want to have as much as possible the same balance of number of subjects as well per group, so we can compare the efficacy of the different treatments as well. So it's both covariates and, if possible, the number of subjects as well. So we can apply that directly, and we have done that in studies to try to see the efficacy of the treatment. So in this case, we use the propensity scores to have the same stratified groups, meaning the same covariates and same number of subjects as well to test the efficacy of the treatment. Here we test the efficacy of surgery, for instance, and this is not using imaging data, but it's been done for many other types of tabular data. Or we can use it as a way of rebalancing our data sets to then apply other subsequent models. So then we have something that it's more fair when we are testing our machine learning models and deep learning. So here is, you can see the propensity score. It's not per se to see the treatment or to see how a treatment has been applied to a sample. It's more to try to balance the groups. So then when we actually apply our deep learning model, in this case, the groups are balanced. So other type of models that we can apply, it's actually causal trees or causal forests. So these are based basically on any tree that we have, any tree method. And what we are trying to do is maximizing the split between the groups that we have that receive different treatments and the control group as well. So if we assume that we have a group A here and a group B, what we want to do is, without any prior assumption, just apply a tree-based model that's based on the features that we have, creates the maximum separation between these two classes and identifies how they react to the different treatments. So one of the advantages of these methods, I mentioned that is the fact that we don't need prior assumptions, but it's also the fact that they can encode nonlinear relationships as any other random forest or tree-based method can do. And basically they have been quite smart. It's not different. I'm not there yet. I will explain the difference in the next slide. So I'm just introducing how is the tree causal model, and then I will try to emphasize the differences between the two. So this has been used actually quite often to do the conditional aberrant treatment effects, to differentiate the two groups of treatments and to pick up more heterogeneity between the treatment effects that we might have. So if we look at the difference between a regression tree, a normal regression tree, and a causal tree, I split it in four main groups. So the first one is the outcome of interest. So in the case of the regression tree, we just have one response variable. In case of the causal trees, and I put it there, honest trees, and I will explain later on what's the difference between an honest tree and a causal tree, but it's the same for both. The outcome of interest is the maximization of the difference between the outcomes of the treatment effects that we have. So we are trying to split the two groups as much as possible to identify how treatment has been applied and what is the treatment outcome that we have in these two groups. Does this make sense in terms of outcomes? Yeah, so imagine that here we have the expectancy of for the response variable where we apply the treatment, so A equal to 1, and for the expectancy of not applying the treatment, A equal to 0, we want to create the maximum separation between these two groups to identify the variable that applies to that as the outcome of the treatment. Guess what? It can be discrete, yes. So in one case, what you have in terms of the outcome variable for the regression tree, what you are trying to do is investigation. Yes, you are trying to split as much as possible the groups that you have, but you are not trying to split based on the outcomes of the treatment that you have. Is the causal assumption that you are making here? You can, but it's no, you can, of course. It's just that here you are putting the causal assumptions that the causal model has in between it. And to do that causal assumption is the fact that each one of the subjects needs to belong to one group, and you need to maximize the differences between groups. Exactly. So that's the two main differences. I'm not saying that they are excluded. Actually, when I introduce both, I like exactly what they are similar. They have the same structure of the tree. They are still a tree. It's just the optimization that you do, and based on the equation that we have here. So you want to basically estimate all of the effects for a given outcome, given a given subject with all of the features,
And then you try to maximize the difference between the two groups, knowing that each one of the subjects need to belong at least to one state. But if we look as well, we can see that the regression trees are mostly used for prediction. So we are predicting the outcome. And in this case, what we want to do, since we are maximizing the separation between the two groups, it's trying to identify the effects that cause that separation between the two groups. So we are not only looking about the prediction that we can make, but trying to look at the effects that led to that maximization of the separation between the two groups. Yeah, and the way that you are optimizing the volume as well. So since you are optimizing the loss function to the separation of the groups, then you look retrospectively at the features that have contributed for that separation. Yes, so here the algorithm is designed to also select operates which minimize the prediction error, of course. And here what we try to do is maximize the differences, as I was saying. And at the end, we need actually to satisfy the conditional exchangeability that validates the conditional models that we have. So when we are talking about tree methods for causality, we have two main branches, the causal trees and the causal trees. I will start with the causal trees. So in this case, what we want to do is partitioning the group into subgroups that correspond to the different treatment effects that we have to maximize the distance between the groups that have been treated with different treatments and maximize as well the heterogeneity that we have in this data. The way that we split and we do the splitting in the trees, it's actually using the same data for both the splitting into the nodes and leaves, and as well to calculate the treatment effect that we have. And this causes overfitting exactly because we are using the same data to do the splitting and the treatment effect from the division. So one way to try to solve that, it's actually using honest trees. So for that, what we try to do is having subsets of data to do the separation between splitting, so splitting into the nodes from the tree to find the best path, but also the estimation of the treatment effect. And this tries to overcome the issue of the overfitting because it decouples what is the splitting of the tree and the resulting treatment effect that we are estimating. So here are these two examples that have leveraged this type of model. So the first one is actually trying to find the best treatment regime using causal trees. So in this case, they try to estimate heterogeneous treatment effects and try to find the nonlinear relationship between the several features that they had. And basically, this study tried to show that we can actually develop personalized treatment models based on trees causal models. On a different hand, we also can try to identify mechanisms of healthcare intervention. So what is the most efficient intervention for a given patient? So in this case, we are not only trying to estimate the treatment effect outcome, we are also trying to estimate what is the pathway and the clinical pathway that the subject can follow. Yeah, in this case, yes. In the later one, not the one at the bottom. So moving from the trees, I will just take a step back for the Bayesian network. So a Bayesian network is a probabilistic graphical model. So Natalya already introduced the directional statistical graph. Here, I just want to emphasize how do we actually compute the probability of certain events and nodes when we have a Bayesian network. So the way of doing that is by doing the decomposition through the factorization of the probabilities for the different nodes. So how can we do that? Let's imagine a very simple network as we have here. If we want to compute the probability of each one of the nodes, what we can do is just do the factorization through the multiplication of the different probabilities for each one of them. So in that case, the probability of A, since it's the parent node, it only depends on A itself. Then if we want to calculate the probability of B, its conditioned, since it's a child, it's conditioned by the parent node, which is A. And at the end, if we want to compute the probability of C, then this is conditioned by both A. And it's like that we can compute the probability of all of the states. So once we have that, we actually can start building more complex networks with different instructions, like this one here. And as I was saying, this can be generalized for any type of network that we have through the product of
one of the states given the current concept that impact this. So if we consider these, what is the difference between a Bayesian network, which is used to actually see the behavior and the effects of something on a system, and a causal network? So the way that we can separate both of them is by testing for the intervention. So if we actually change something in our network, we transform from a Bayesian network to an interventional one. Meaning, in this case, I know that the floor is wet and it's slippery, and I know that we have a sprinkler, and we also have some seasonal rain. We can model all of that through the probabilities of getting slippery based on all of the rest of both. But now I want to know if the floor is wet and slippery because it rained or because it actually there was a sprinkler on. So to test that, it's through the interventional part as Natalia presented before. And basically what I test is without the sprinkler on and with the sprinkler on. And by testing the two different networks, I can see the effect of the intervention and estimate if the intervention actually occurred or not. Makes sense? And that's the main difference between the two of them. However, this kind of model still lacks something, which is the ability of model counterfactual. So it doesn't allow us to go retrospectively and actually simulate other causes and effects that we might have. So one way to overcome that is using a different type of models, but I just want to emphasize here that Bayesian networks and causal Bayesian networks, despite the fact that doesn't allow us to simulate the counterfactuals part, actually have been quite extensively used for medical imaging analysis to try to determine what is the impact of different conditions in the body. So just by looking at is this condition happening or not, and how can I define the causes effects that have been linked to this condition. Here we just have a distribution how they have been used so far. But as I was saying, these models can be used not only to find the diagnosis itself of different pathologies, but we can use as well to see, for instance, which kind of image am I looking at and which kind of relevant features I have from this image. So in this study here, we have a Bayesian network that is used to just do classification of image modalities. Differently, we can use it to do, for instance, the testing of the effect of different interventions. And here we are trying to do the modeling of the risk of developing preeclampsia and trying to see all of the factors that contribute to that through a Bayesian network model. So as trees and as propensity scores, we can use it both to describe the system or to predict the intervention and the outcome of that system. So the last type of models that I want to talk to you about, it's actually the structural causal model. So the main difference between the structural causal models and the causal Bayesian networks is the fact that here we can actually model the counterfactuals. So to do that, and here I give an example of a graph like this one, instead of having just the probability of moving towards one of the nodes here, these probabilities model towards structural functions, structural equations. So basically, we can model with f being a function that models x here. So what's the probability of happening here? We can just model out the probabilities of the system. If we look at the terms of the equation, the probability of the variable of the graph for each one of the x's is exactly the same as the one that I show for the Bayesian networks, with the difference that x now, it's not just the probability that we observe, it's actually modeled by a structural equation that we can add or a structural model. So in this case, we can do more complex kind of analysis. So here, for instance, in this paper, they study the causal effects on survival for glioblastoma. So in this case, what they try to study is what is the impact of changing different treatments retrospectively to see how can we treat glioblastoma, specific type of tumor. Or we can do it again in a different way. So instead of just trying to optimize what is the best clinical pathway for a subject, can we actually go retrospectively and study what would be the impact of changing the clinical pathway for each one of the subjects that have come to the hospital, in this case for the ICU, and try to study, for instance, the causal effect of applying oxygen therapy or not. So again, the main advantage of this type of models is actually try to simulate what didn't happen. So inside of the structural equation modeling in specific, we have another type of models, which is the structural equations modeling. In this case, we are trying to implement a statistical analysis through causal hypothesis on a system to try to model what is the effect of applying this cause to produce this effect. So these type of models, they rely on latent variables, observable variables, endogenous and exogenous. The ones that we need to pay more attention to, it's actually the fact that endogenous ones are the variables that actually impacted by others in the system, and we observe them. In this case of the exogenous, we don't observe the ones that we note, and these are external to the itself. So the assumptions of this model is the fact that the data needs to be multivariate, normalized, normal distributed. So it needs to actually have some linearity. So the structural equations model differ as well from the structural causal models because they assume linearity. They need independency between the observations. So each one of the observations need to be independent from the other one. We assume as well that there is no missing data. So these kind of models cannot be used in the presence of missing data or for imputation, for instance. And they require sufficiently large data sets so we actually can capture the statistical dependency between the different covariates and the different samples. And lastly, they also require minimal multiple linearity. So actually, and this brings me to my work in specific, I have been applying structural equations models in specific to study the relationship between twins. So in this case, I have imaging data from pairs of twins. And what I try to do is to find the similarity between these twins and actually what is the causal effect of variables like genetics, environmental variables, and unique environmental variables that might condition these twins that cause differences in phenotyping of the brain. So to do that, I designed my specific model, and basically I just try to estimate the causal impact of each one of these three group of variables in the brain phenotypes that we have. And this brings me to the final of my part, to the end of my part. So if anyone has questions, yeah.
And from my understanding, it's decided, and this idea was to use a double G leverage from different domains. To use the because you can't establish clear cause and effect reconciliations in economics means to human behavior is messy and have ancient values. But in terms of biological science and mental science, how we establish clear mechanistic relationships and we can be doing for hundreds of years just due to having the science for experimentation. So and I think this question helped clear the understanding what advantages does this method have over in silico learning in vitro and in vivo studies? Because in those studies, you can develop clear cause and effect relationship while yes, similarity of the cause and effect, but still statistically some nature.
Yeah. So I will separate what you were saying. So basically, there are different types of models and they are meant for instance, the structural causal model. It's not meant to be used to actually describe the system. That's used for the equations. And in that case, these kind of models are not meant to just be applied to try to simulate in silico. These ones you need specifically to try to explain what you are observing. If you want to do in silico simulation, for instance, lots of causal models actually have been used to do some kind of generation of data simulation, for instance, and we will be talking about that later on, where instead of you just trying to describe what you are seeing, you can generate the data according to the prior assumptions that you have and the causal assumptions that you also have to have exactly the data you want to study and as well to do simulations of different treatment effects, for instance, or different response to treatment, so on and so forth. Does that answer your question more or less?
Well, exactly. There's a bigger picture of like what bodies does this have whatever those basically it's like a reason why I didn't even know there was hearing medicine as much concern. So what was the reason why people started doing medicine?
So the reason why people do it in the field of medicine is to find the correlation, not the correlation, the causal effect
between what you are observing and the different variables that you might have affecting the system. So let's imagine you want to test a treatment effect. And as Natalie was saying, doing random clinical trials, randomized, it's not that easy due to ethical reasons, due to the number of subjects that you actually can test that on, so on and so forth. So by doing these causal models, you actually can test the same assumptions in a controlled environment-ish, because we are still dependent on the assumptions that we are doing about the system that we are studying. And due to that, you avoid all of the downsides of the clinical trial or observational study that you might need to put in place. So people have done it for a long time. There are reasons for it. And the main reason is you can study a full system by doing simulation of different options and test for the hypotheses that you think that they are true. For instance, you might even think, and this is a pretty silly example, but let's assume that you know that smoking causes cancer. That is your assumption. You can test that by testing all of the different causal behaviors and interactions that you might have between smoking, age, treatment, so on, so forth, all of the other variables that we wouldn't be able to control to test these hypotheses that you have. Does it make sense? Yeah. So, it's like danger. Apparently, doing the information that explanation, but then the more information sense. And the more information you give people, they think then that they should trust it. But if it's wrong, yeah, what potentially wrong? 100%. So that's something that we will be discussing at the end of the presentation, which is what are the challenges and the risks of causal models. The problem is some people interpret causality as correlation and vice versa. You might be giving the clinician, I think this is the cause of something, and this is causal related, but it might be just a correlation. This is highly dependent on, first of all, the assumptions that you are making while designing the model, and this is why it's so important to be cautious on that, and also why you need to design different models and test different hypotheses to then have the differential of the results. That's another question. You need a large amounts of data to do this kind of model. So here I'm presenting machine learning one, so not as data as you would have in deep learning that we will present next, but still it requires a large amount of data for sure. And as heterogeneous as possible. So I find it super interesting to see the effect. Like, and it's what you're saying that in economics, you need to say that in medical imaging, so it's even more, yeah. I agree, but that's the reason as well that you need to select the type of model for what you want to do. You can do very simple things like the propensity ones where you don't have any assumption and the only thing that you want is to have as stratify as possible to then study the effects that you might have. Or you might go for the structural equations model, which are more complex ones but are full of assumptions. You are the one designing the model. At the end of the day, these are parameterized models. And in that case, you are relying on the clinical assumptions to prove if that is true or not, and to see if you still see the effect given the assumptions that you are making, but it might lead to wrong results and bias because your assumptions were biased at the beginning. Just one correction that I forgot to mention. I was trying to be cautious on time. But these kind of models, they don't rely on correlation estimations. They could rely on covariances, for instance. So there is also that slight difference when we are building the structural equations models or the causal analysis. Covariance is one and conventions. Yes, nice. Yeah. Yeah. So for instance, in these kind of models, the structural causal ones, you have the data prior to the intervention. This is actually the exogenous noise. If you remember when I was talking about endogenous and exogenous variables, it's the type of data that you have without knowing where the data comes from. So it's not intervention, it's intervention free, and you try to model that. So of course that you need to have data before the intervention, having the intervention on, and then you can also simulate the effect of the intervention there. So yes. Oh, my question on that say it again, sorry. So let me click before that. Yes. So in that case, you are on the realm of the average treatment effect models and this type of models where you actually try to have two groups and compare them. So one group didn't have intervention and the other group had intervention, and you compare between the two. So I will pass to the next subject.
So I will introduce some deep learning approach for cultural modeling. And so why people using like deep learning for cultural modeling is because like deep learning models are more suitable to learning spurs thesis correlations and amplify biases. And also like deep learning models can better like model like complex data and high dimension data. So that's why like we would use deep learning. And also causality can improve like the transparency, fairness, and robustness to deep learning models. Um, and also there are like several like key advantages for it. So for example, like in causal discovery, like it can integrate like observational and interventional data, and also even with some like hidden confounders, and to generate like more accurate causal graphs. And in the causal inference, like neural network can help like reduce estimation biases of causal effects due to their strong fitting capabilities. So in this like images, we can see like the four orange arrows can see like the neural network deep learning can contribute to like the representations, discovery, and also the inference. So first I would talk about like the causal discovery. So it's quite crucial in medical images. So for example, like usually when doing like the deep learning method, we first like extracting the features and then apply the causal discovery algorithm like the traditional one. But we first like using the CNN or kind of feature extractor to extract it. And for example, like this method can tell us like which one are crucial or which one are actually cause to the disease progression. So the first example is when people doing with using deep learning is like they use two pair of data and use the priori knowledge to predict whether they have the age, like we talked before, like the pH graph. So you using using the priori knowledge, we can like get the high dimension data to project to like whether they have age, and then use the uh, causal risk framework during the inference to see like if it really has the causal effects. So in this case, like we can deal with like very massive data. For example, like here it would like have like over 5,000 variables, and also for the cell it have like even 8,000 variables. So in this case, we can like deal with more like high dimensional data. And then I would talk, sorry. It is actually here is not a real image. It's like the heat map of the, or not heat map. It's like the, yeah. It's like the table data translated to like image and then producing. Yeah, and then I will talk more about the counterfactual generation. So in deep learning, especially generative models, it used to generate seismic images under hypothetical scenario. So it's always like what if analyzed. but when I was like searching for the articles for this, I found it's really hard to do like causality in images. Like most of the time, it's more like covariance actually. Yeah, but this how people doing right now. So I would simplify the question as into like different models. Like so basically for generation model, we have like those four types, GAN, VAE, flow-based models, diffusion models. But for here, like for the previous two or like the mainstream for the causal or counterfactual generation is GAN-based or like the combination of VAE and GAN is because like we don't have the ground truth for the CISIC data. So the only thing we can rely is like the classifier or like the classifier, it can like detect which distribution it belongs. And then we can like rely on the classifier to optimize the generation. So the first is obviously like the GAN-based method. It has like high quality, realistic outputs, and also flexible and also like easy to get condition control. So here is like the first one is like I think this paper comes from George School. So basically.
Expedition was actually given died into projects.
Yeah.
Renaming it manufacturing values. What's the difference between that and a condition and like something in the model itself, which it's a counterfactual.
I think ba basically like quite similar. Yeah, it's all count on the like the domain label, like the classifier to help like the model to generate like the true distribution of your target or like counterfactual label. Yeah, so here is like the first one. So here there would be like age or sex, like those attributes. And the second one would be another like improved one is like it's used both like in intensity transform and spatial transform and put all the attributes over here. So basically like the same, but they like get like two transform. One is intensity transform, another is spatial transform. And so here is like the output of it. And here would show like a little bit causal thing. So here is sorry. So here is like use the VAE-based models, and during the Latin space, we can like embed the causal graph. So for here is but I have viewed like many methods for like counterfactual generation and also use like the SCM models. And it shows like usually people can only control like several variables. So like here is like ring volume size, and V is like the ventricle size, and the G is like the gray matter volumes, and A is age, and M is like the mini mental state examination. So here he got like causal graph and then put it into the Latin space. So here we can see like by controlling those graphs, we can see like if we do like the MMSE, like the examination, like if we get the score like lower, which would show like you are you got a higher chance like you got 80. So it shows like your ventricle got bigger. And and for this is like so usually like the brain size changed by like the sex. So it's like if you change between women and men, like your brain size would change. So it's really simplified, but that's how people do or how people can do right now. Yeah. Yeah, it's it's achieved by like using like style gain using 3D uh, and uh, and then I would introduce more about the flow-based models. So normalizing flow is a class of like generative models using machine learning to model like complex data distribution. And less people use it for like image generation because it's really easy, because I have trained it a lot of times. It's like really easy to collapse and it's really easy to like overfitting. But for like counterfactual generation or like causal modeling, like normalizing flow is actually like plays a good role during the latent space. If you use like VE as a base network and do the causal thing on the latent space, flow network can actually like have good result because it's like due to its I think it can transform back. So what you transform into the latent space, you can get exactly what you want back. So I think that's the like advantage of flow-based network. So I think in 2020 NIPS and they propose like a deep structural causal models for tractable counterfactual inference. And it's also like combined with VAE. So the normalizing flow is doing in the latent space. But this one is basically the same as the last one, just use normalizing flow over here. So here is like the ventricle size and the brain volume size, and here is like the sex and your age, and here is like the counterfactual generation shows like okay, it's actually like changing those variables. And also from the images it shows it's but it's hard to say like okay. Yeah, but it's also like hard to like show on the numbers. It's like, okay, I changed brain, like for example, from 65 years old to 75 years old. Like, how should I use some like numbers to show they are like actually the same subject? Yeah, so yeah, this is also another problem for like counterfactual generation is like there is not much benchmark for counterfactual generation because it's really hard to like validate your models because there is no point choose for your counterfactual generation. Yeah, and also like flow-based model or like causal thing can also do like harmonization. So in this paper, it's like to improve the generalization of machine learning models by harmonizing the medical data collected from different sites and protocols. Yeah, and this one is actually, I don't want to put it over here because there is very, very few like diffusion models which can like insert causal graphs or like structural causal graphs. But this one is like more approximate to our like counterfactual generation. So here is like we can just regard like their whole here would be like a control net which would like give like the subject information, and what they got here is they got another model like to predict okay what if for example if you are 65 years old and we want to see what how you look like at 75 years old, and they choose like six or five related area based on prior knowledge, and then like to get more accurate. Yeah. So it shows like it's more accurate because the good thing about diffusion model is like it can generate more not accurate, more clear models images. And also some people thinking about like large language model because like it can read a lot of things. So many people also try, like, for example, I give it a book and ask LLM to read it. And if it can like make better reasoning or like predictions, and the result shows like basically not much improvement. It's still at like poor skills. So maybe it's like a uh, future direction for everybody. And here would be the benchmark. I know this one is not that like good, but it's still like a very rare like benchmark I can find. So this one is like for it's on 2D slices, and so they use like 4 key metrics uh, to measure like how good your generation model is. So the first is composition, the second is effectiveness, and the third is realism, and the final is minimality. So basically, uh, the causal graph is not that satisfying, but it also is like a very rare benchmark. And here is how they test it. It shows like the HVE like basically outperforms every other methodologies, but HVE is not like a typical uh, model. It's just like a exploration of VAE. So basically, the difference between them is like we use a single flat data space, which may struggle to model highly structured or hierarchical data, and HVE like employs a deeper and multi-level latent structure. So that's basically the difference. And here I can like recommend some GitHub repo if anybody want to use. It's like I think for machine learning, like the causal machine learning is quite good, and they have tutorials, so it's quite easy to use. And if you want to do like medical image data, I think Monai, like the generative model, would be the best because they have like plenty of tutorials. I tried most of them and they definitely work. So I think it's worth using it. Yeah, and this one is I recently found is using normalizing flow, uh, just modeling like tabular data, but it's really good to use. You can use CPU or GPU, and it will be easy to also like construct the causal graphs because I tried is like although they don't have the tutorial, but you can put those informations to GPT and ask, okay, I want to use this repo and please like follow this instruction and build me a causal graph. And he will actually do it, and then quite good. Yeah, you only need to like add it a little bit and it's working. Okay, let's keep going to.
So this is a very quick one. We just wanted to highlight some of the current challenges while defining causal models and also what are the future steps that we think that might be relevant for this. So one of the first challenges that we encounter while doing this overview of methods is actually the plausibility of the assumptions. So lots of these models rely that we meet all of the assumptions that Natalia was presenting at the beginning, but actually that doesn't happen. And sometimes we need to actually either drop groups when we don't have enough information or don't fulfill the assumptions, or try to do the realization of some assumptions. So in one case that we have into account here is the fact that in medical imaging problems or medical problems in general, the cyclical graph assumption sometimes doesn't hold at all, and we have loops everywhere. So this is one of the things that we need to have in mind while establishing these models. Another thing is the rationale of the model that we are using. So as we were saying, there are models to try to find the graph. Specifically, there are models that actually try to model the observations that we have, others that try to assess what is the treatment effect. So when we are designing the causal model itself, it's really important to pick the specific type of model for what we want. Do we want to test counterfactuals or interventions? And this is really relevant when picking the right model that we want to apply. And one of the things that we already mentioned and touched upon it is the requirement for large and good quality data. So causality in specific and causal models is highly impacted by biases that we might have in the data and biases in the assumptions that we have as well. So having large data and good data is highly important when we are testing the assumptions that we are basically looking for. And basically, it's also the uncertainty quantification. So the majority of the machine learning models, and nowadays we have a bit more work done in the uncertainty quantification, but the majority of them still provide quant estimates. When we are dealing with causal models, the quant estimates actually can lead to erroneous conclusions and highly biased conclusions. So actually, it's really important to try to do some uncertainty quantification while we deploying these machine learning models into causality analysis. So these are the main challenges that we wanted to highlight. What we think that is relevant in terms of next steps of how can we actually improve the causal models that has been developed so far. So the first thing is we can introduce causality in deep learning models to try to actually find complex relationships into our data. Another thing is, as I mentioned just before, relaxing assumptions, mainly including and measured confounding and selection bias, something that we need also to work on while developing this model. So we know that these assumptions won't hold, so let's try to develop models to face that and to actually tackle that part. Another thing is the fact that we can try to develop more robust models and interpretable as well, and specifically in deep learning fields using causality. We can use causal models to actually deal with missing data and to do the imputation on missing data. So as I was mentioning before, there are models that won't work on that. For instance, the structural equation is one, but the structural causal model itself, or even the Bayesian network, might be really useful to do the imputation of data. We have seen it, for instance, for image generation, but we can do it as well for tabular data simulation. And something that is really relevant as well is the fact that causality itself is prone to develop models like that, which allow us to do personalized models for the individuals. So it moves us towards the personalized medicine part and away from the group analysis. So this is highly relevant while using these models. And the last one, and this is something that I find really interesting, is the fact that we can use these models to actually do synthesis of images. And I'm a bit upset that Mark left, and something that he was mentioning is data augmentation. Yes, we can do, and we can use causal models to do data augmentation, given the hypothesis that we already have drawn for our specific treatment effects or disease that we are studying in specific. And one of the studies that I found really interesting, and this has been published as well in Neurips, is a group from the Alan Turing Institute, and they have been doing lots of synthetic data sets for medical and healthcare problems. So it's not imaging-based methods. Most of them are to synthesize synthetic data, but they do the synthesis of the clinical data based on the causal inference that they already drawn for different pathologies or different treatment effects or different pathways in the clinic that patients might follow. So it's kind of a robust way of trying to generate synthetic data for our applications. And that's it. That's the end of our presentation. I hope that you enjoyed it.